and visible?
Yes.
Great.
Okay, so let's welcome Marc Besson. He's from Beijing International Center of Mathematical Research, and the topic of his talk is twisted affine Schubert varieties and twisted affine Demazure modules.
All right, thank you very much for the introduction, and thank you very much for the opportunity to give this talk. So my plan is to break the talk into a couple pieces. So the first piece will be notations and motivation. The next step, where we start getting into kind of the meat of the talk, will be I'll go over the Frenkel-Kac-Segal isomorphism, and then a geometrization of this isomorphism, which is due to Zhu. So the geometrization of this isomorphism was done by Zhu in the untwisted setting. And so the goal of this work, oh, I should briefly mention, of course, that all of this work is joint with Juzhu Hong. And so this is a result that is in the untwisted affine Schubert variety world, and the aim is to generalize it to the twisted case. So the third step, I'll kind of briefly go through twisted affine Grassmannians. And lastly, the result, which is maybe I'll say a twisted restriction isomorphism. Okay, so before I even make any notation, maybe I want to just give a very broad word here about the way that I'm thinking about these objects. So for motivation, in the finite case, we have these objects called Schubert varieties, which are inside the flag variety for G, say a semi-simple group over C. And the geometry of these Schubert varieties is very closely related to representation theory. And in general, there are two kind of very broad ways to study it. In one direction, we can study the geometry and the singularities of these Schubert varieties using, say, perverse sheaves or intersection cohomology. This is a little more topological. If we study in this fashion, then we get Kazhdan-Lustig polynomials, for instance. And from the Kazhdan-Lustig polynomials, we get decompositions of Verma modules. So maybe I'll say multiplicities for Vermas. So from the geometry of the Schubert variety, we take intersection cohomology, and we understand some representation theory. There's another kind of more algebra geometric way to study this, which is to take global sections on the Schubert variety of certain line bundles, L lambda. This leads to, for instance, the Demazure character formula and things like that. So two different pieces of the geometry of a Schubert variety that interact but are slightly different. And we have the exact same story in the affine case. I haven't really defined anything, but I just want to write kind of the analogous statement. So these affine Schubert varieties will be written ger lambda G. In one direction, we can study perverse sheaves or intersection cohomology. And if we do this, we get geometric satake. On the other hand, there are very natural line bundles on the affine Grassmannian. And if we study global sections on affine Schubert varieties of these line bundles, then we get what I'll call affine Demazure modules. And the combinatorics that are related to these are things like let's see, some McDonald polynomials, non-symmetric McDonald polynomials. So I just want to point out that in this big paradigm, this work is going to be focused here. So focused on line bundles on these objects. Okay, it's kind of a crime that I've been saying all these things without defining anything. So maybe I'll get to the definition part. So I suppose, yeah, I actually probably shouldn't permit any questions yet. So I'm going to let G be a semi-simple algebraic group over C. And I'm going to fix a torus inside a Borel inside G. So we have our standard construction. So we have the Weil group, normalizer in G of T, modulo T will be our Weil group. It's a Coxeter group. What else do I need? I need the character and co-character lattices. So we have the co-character lattice of T. This is going to be Homs from C star to T. And similarly, the character lattice will be Homs from T to C star. Okay. I think this is what I need from groups over C. So in the affine setting, I'll be working very often with formal Laurent series, and I'll use K to denote the field of formal Laurent series. And I'll use O to denote its ring of integers, can be described as formal Taylor series. Any questions? Is that okay? Is my handwriting legible? I'll take that as a yes. Let's see. So already I think we can define the loop groups. Since I'm going to be working kind of in algebraic geometry, I need to be careful to do it sort of geometrically. So I have my loop groups, which I'll define as functors. So the set of R points of the loop group is going to be G of R T. So I take my group and I have entries which are formal Laurent series in over with uniformizer T, say, and over the ring R for R C algebra. And then I have the art group, and I define its R points to be G of R double bracket T. And already we're ready to define the affine Grassmannian. So the affine Grassmannian GER G is going to be the sheaf quotient. I can take an Ital quotient or something like that. So it's defined to be the quotient LG mod L plus of G. Let's see, what should I say? Should I say anything more here? Oh, I should say that when you take the C points, you get back something kind of very familiar. So, you know, GER GC is equal to G over formal Laurent series mod G over formal Taylor series. Oh, I should use G of K mod G of O. What's the notation for if you don't use it? So these are the C points of the affine Grassmannian. Okay, I should also mention, of course, that for every co-character lambda inside the co-character lattice, lambda will induce an element. So this induces an element, which I'll denote by T to the lambda inside the loop group. And I can write its image, T to the lambda, inside the affine Grassmannian. So I have these kind of distinguished elements inside the affine Grassmannian associated to every co-weight of my torus T. And this map is just given by taking the image lambda of a uniformizer T. This is going to be inside T of K, basically. And then this includes inside G of K. Okay, this is mostly the notation. I should mention it's very important for some of the proofs, but probably not so important for the talk, is that there's a moduli description of the affine Grassmannian, namely the R points of the affine Grassmannian can be described as sort of tuples of F, a G-torsor, and beta, a trivialization. So F is a G-torsor on the R disk, dr, and then beta is a trivialization. You restrict your G-torsor F to the punctured disk, dr star, and this is isomorphic to the trivial G-torsor F naught, restricted to D to the punctured R disk once again. So I just bring this up because several of the proofs eventually will rely on things like valence and Grünfeld Grassmannians, and this is the correct kind of way to think about Grassmannians if you want to globalize them and get objects living over a curve, for instance. Okay, any questions so far? Is this all right for setup? Okay.
Okay.
Oh. Was that my own voice echoing or a question? Probably that was my own voice. Yes. Okay. So I want to discuss some of the geometry of these affine Grassmannians. So geometry. So first of all, G will be an in scheme. In particular, it's infinite dimensional over C. Moreover, if G is reductive, then that will imply that G is int projective. So I'll be working kind of with two groups. I'll be working with G semi-simple, and so certainly then I'll have that G is int projective. But I'll also be working with the affine Grassmannian associated to T, a torus. And then I have the following result, that the affine Grassmannian G is reduced if and only if the Halms from G to GM are trivial. So in particular, what this already says is that the affine Grassmannian associated to the torus will be non-reduced. I'll come back to this point. I want to kind of belabor this a little bit, but for the moment, I'll move on. The next thing is that this is kind of maybe the topologist's reason for thinking about loop things, is that we get a description of the components in terms of the fundamental group of G, the algebraic fundamental group. So x lower star of T modulo, I didn't introduce the co-root lattice. This is the co-root lattice. Really, what I should probably put here is the loop group, but then I'm quotienting out by something that's contractible, G of O. So I get this statement on the components. And then the next important point that I want to belabor a little bit is that if G is simple and simply connected, then we have a good description of its Picard group. The Picard group of G is Z. Okay, this is the second point that I want to kind of go over with a little more attention. So these are some of the facts that we have. Let's first return to the reducedness. So a very important example for me and what follows will be the affine Grassmannian for tori, and the simplest example is the affine Grassmannian for the multiplicative group. So the first thing that let's look at the C points. So GMC, how I can produce a C point is I first take F inside the loop group of GM, and so F can be written as some formal or some non-zero Laurent series. So maybe a1 t to the, I don't know, some n1 plus a2 t to the n1 plus 1, etc. Okay. So this means, and I can always, so I know that a1 is non-zero, so I can factor this as being equal to t to the n1 times a1 plus a2 t to the n1 plus 1, etc. And this piece is a formal Taylor series. It's invertible because a1 is non-zero. a1 not equal to 0 implies this thing lives inside L plus GM C. And so if this piece is the quotient, then we see that there's a natural map from the affine Grassmannian for the multiplicative group. So GER GM C is going to be isomorphic to the integers, and that's given just by sending such an F to N1. Okay, so the reduced subscheme of this affine Grassmannian is a discrete scheme that is parametrized by the integers. On the other hand, let me remark that it's very easy to produce nilpotents here. So now, for instance, let me look at, say, a point in LGM of C, say, x modulo x to the k. So I make some C algebra with a nilpotent. Then there's a very easy way to make, to have elements involving nilpotents in here. I could write, for instance, some point that looks like a1 t to the n1 plus a2 t to the n1 plus 1, some sum as I did before. And then I can always multiply this by 1 plus x t to the negative k. Right? So this is a nilpotent. A nilpotent plus a unit is invertible. So indeed, this is an element in LGM of, well, I don't need to write it again. This is an invertible element inside formal Laurent series over this ring. Once again, I can factor this as being x t to the negative k plus 1 times t to the n1 times a1 plus a2 t to the n1 plus 1. So this thing right here lives inside L plus GM with my CX modulo x to the k or whatever. So the point is that the class of F inside the affine Grassmannian is going to be a non-reduced point. What should I write? Cx modulo x to the k. This is a non-reduced point supported over the closed point, which I'll call kind of N1, right, from the earlier thing. So in other words, the picture that I have of the affine Grassmannian for GM is of the reduced scheme is just a copy of Z, and then each point is kind of infinitely fat in the sense that each point you can produce nilpotent points with nilpotents of arbitrary order supported at each of these reduced points. So this is, on one hand, a kind of simple structure, but it's important to take the full non-reduced in scheme structure. Okay, any questions here?
Yeah, I did have a question because, I mean, the way you're sort of phrasing it, I mean, this is not the way these nilpotents would work, they would be, you know, for a scheme to be non-reduced, you want some kind of functions that are nilpotent functions. I mean, it's not that the point itself is nilpotent, sort of something. And then what's the, and I guess I don't completely understand. The other thing is that this scheme C of X mod X to the K, I mean,
so this ring, yes.
Yeah, that's not the same as C there. So how are you thinking of that mapping to your Grassmannian with just coefficients in C, your GRGM C? Like,
So
that mapping, are you thinking of the C mapping into that, or are you thinking of that mapping to the one with C? I'm a little confused actually how this.
Yeah, sure. So first thing that I'm doing is I'm just producing a point inside the loop group LGM of C. So the loop group of GM and R points of that for R C algebra is exactly the collection of invertible formal Laurent series over that ring.
Right, okay, that's fine.
So this thing that I have here at least gives me an element inside here for the correct R.
For that correct R, that's right.
And then I know that the affine Grassmannian is a quotient of these things. So the image of this element inside the affine Grassmannian will just be some element that is supported over N1.
But is it the affine Grassmannian with coefficients in R, or is it just affine Grassmannian?
Yeah, the affine Grassmannian with coefficients in R, yes.
So it's not the, so above you, you're saying the affine Grassmannian with coefficients in C is a, are you thinking of this as like the, I mean, maybe I don't want to divert you too much, but
no.
I mean, are you thinking of GRGM of C itself as an in scheme? And then you're not, this is different than that.
So here I should say that I'm thinking of GR GM with no thing as an in scheme or a non-reduced in scheme.
Okay, I see.
And how am I seeing that? I'm testing it with either C or a C algebra with nilpotence and seeing what I can produce. And here I have a non-trivial morphism from a C algebra with nilpotence into this scheme.
I see, okay.
Yeah, sorry if that wasn't clear. That's a very good question.
Okay. So the non-trivial homomorphism of a C algebra with nilpotence into that scheme is basically meaning that the scheme is not reduced, is what you're saying.
Exactly, exactly.
Okay, thank you.
Mm-hmm. Great question. Okay, the other brief thing that I want to go back to is the Picard group. So now let's return to this statement about the Picard group of GR G being isomorphic to Z. So since G will always be reductive, either the torus or G semi-simple, both of those will be reductive. So I know that this is projective, which means that one of the generators of this Picard group must be ample. So one of the generators is ample. And I'll denote that ample line bundle by L. So L will be the ample generator of for G. So the thing is that one would, of course, like to describe a representation. So one wants some action, say, of the loop group on the cohomology spaces that one would produce via this ample line bundle. So we have G, L, and take duals. This would be the standard construction that one would make to produce representations of a group acting on a homogeneous space with a line bundle. So unfortunately, LG only acts via projective transformations. So this doesn't actually produce a representation of LG. This doesn't work, so only acts projectively. So the solution to this is to pass to central extensions. So we can produce a central extension, which I'll denote by G tilde. So this is kind of two extension. This is an affine Kac-Moody group. It only really appears because now this will actually act. So this affine Kac-Moody group now will act on the cohomology spaces of the affine Grassmannian L dual. So the affine Grassmannian is also a homogeneous space for this affine Kac-Moody group. And also there's an affine Kac-Moody algebra, G tilde, which will similarly act. One more thing that I want to mention here is that once we've passed essential extensions, that introduces a new parameter called the level. So if I have essential extension that looks roughly like this, C star times C, maybe I'll use as, I'm forgetting the derivation, but I'm just going to continue doing that. So if I present this as essential extension, then what I can do is I can, so for L inside the Picard group of the affine Grassmannian, I can pull L back from the affine Grassmannian to the loop group, and then I can pull it back to the Kac-Moody group, and I can restrict it to the central extension. And this central extension will act on this line bundle via a character. And so what this does is this defines, so C, this defines a homomorphism, which I'll denote by C. Here, this can be also written as the central charge from pic for G to Z. And it is a fact in the untwisted case that the central charge of the ample generator is equal to 1. But I should mention that in the twisted case, this is not necessarily true. And this is one thing that has to kind of be repaired in the twisted case. So there's a thing floating around called the level, which is produced by letting your central copy of your central copy of C star act on your line bundle. So that's maybe something else that I wanted to mention. Okay. Now, still some more stuff to introduce. So associated to, so I have my torus, which includes into G, which this will induce a T action of my complex torus, a T action on the affine Grassmannian for G. And here is a very important fact, is that this action of T on the affine Grassmannian induces an isomorphism. This induces an isomorphism from the affine Grassmannian for T, which is going to be isomorphic to the affine Grassmannian for G when you take the T fixed subscheme. Sub-in scheme, maybe. So Gur T behaves very much like Gur GM. So this is going to be an in scheme that is kind of arbitrarily non-reduced. It's supported on a discrete scheme, which is given by the co-character lattice. Gur T is a reduced in scheme, but when I take the T fixed subscheme of this, I get this isomorphism. So it's very important here that I'm remembering the non-reduced part here and the schemy fixed subscheme construction here. It's certainly not true if we take reduced subschemes. Okay, so this will be very important in what follows. So finally, I can introduce the actual affine Schubert varieties. So now to affine Schubert varieties. The Cartan decomposition implies that for G semi-simple, I have a decomposition. Gur G will break up into a union over all lambda inside x dot of t plus g of o, t the lambda, g of o, mod g of o. So this thing right here will be called a Schubert cell. This is some smooth, finite dimensional space. It's an orbit space. And the Schubert variety will be the closure of such a thing. Maybe I'll call this ger lambda g. And then the Schubert variety will be the closure. So ger g lambda bar, this is equal to, well, the closure of the Schubert cell. So the geometry of these is very well understood. It's very combinatorial. So first of all, these have a stratification. So well, maybe first dimension. So dimension of ger g lambda bar is equal to the pairing 2 rho on lambda. Remember, lambda is a co-weight. We have a stratification, namely ger g lambda bar is equal to a disjoint union overall mu less than or equal to lambda mu inside the dominant co-weights of ger g mu. And moreover, we know what the t fixed points of these affine Schubert varieties are. So we have a t action. Here t means the torus over C. This acts on ger lambda bar G. And the t fixed points are precisely the classes t w mu inside ger lambda bar closure, where here w is in the Weil group and mu is less than or equal to lambda inside the dominant co-weights. So any questions here with the geometry of these Schubert varieties? Or kind of more earlier stuff? Any questions so far? More questions? Okay. If not, then there's kind of one more piece that I need to get to. So now we can proceed on to the Frenkel-Kac-Segal isomorphism, but there's one more thing to introduce. So the Frenkel-Kac-Segal isomorphism, So I need Heisenberg algebras. So I let T hat be here I'm working with Lie algebras, be the central extension of the loop torus or TK. So here T is the Lie algebra of T. So this has the following bracket. The bracket X, say tensor F, Y tensor G. Here X and Y are inside the torus and F and G are formal Laurent series. This is going to be equal to the normalized pairing, or the restriction of the killing form, say, to T times the residue at T is equal to 0 of df times G times C, the center. So T hat is a central extension of this abelian Lie algebra with bracket defined as follows. So there are kind of two things that an algebra or a group should satisfy to be called a Heisenberg group or Heisenberg algebra. One is that it should be a central extension of an abelian group or an abelian algebra. And then second of all, there should be some sort of Stone-von Neumann theorem, which classifies the representations. So here is the analog of the Stone-von Neumann theorem, that the representations are very easy to describe. So we can introduce the Fock modules, which are going to be pi, lambda, comma, k. These are defined to be the induced modules ind from T of O plus C times the center to T hat of the copy of C, where the torus, the C torus acts via character lambda, and the center acts via character K. So all the representations of these Heisenberg algebras are going to be of this very nice form. Okay, and now I can state a weak form of the Frenkel-Kac-Segal isomorphism. So this is due to Frenkel, Kac, and Segal in, I believe, in 81 maybe. So this is, and from here on out, the groups they'll be working with are types ADE, so simply laced. So the theorem is that if I take the space of global sections on the affine Grassmannian and my ample generator, this is isomorphic to a big direct sum for all now lambda inside co-weights of T, these Fock spaces, iota lambda 1. Okay. So really what this is a branching theorem. This is a branching theorem for the Heisenberg algebra, which includes into the affine Kac-Moody algebra. So it's describing the decomposition of the basic representation in terms of these Fock spaces for the Heisenberg algebra. In particular, the fact that all of these Fock modules have the center acting by 1 is related, or basically the same as the fact that the line bundle L has central charge 1. And this is going to be a big sum over all elements inside the co-weight lattice. And then this iota maps elements of the co-weight lattice to the weight lattice. So this is the branching result of Frenkel-Kac and Segal. And now I want to describe a geometrization due to Zhu in, I believe, 2007. The geometrization has the following form. We have a restriction map from global sections now of our affine Schubert variety associated to lambda L. This, I can restrict this line bundle. So L is a line bundle in the affine Grassmannian. I pull it back to this Schubert variety, and I can pull it back further to the T fixed subscheme. And I get a restriction morphism to Ger G lambda bar T fixed L. So this is restricting global sections of L to sections on the T fixed subscheme. And the theorem of Zhu is that this restriction map is an isomorphism. I should remark that this is proven by Zhu in types A and D, and many cases in type E, or many cases for E6, E7, E8, but E6 was completed by Juzu and I. And this does not hold all the time. Well, it's conjectured to always hold, but it is not yet proven in all cases for E7 and E8. So some remarks is, first of all, this space, H0 for lambda bar G, L, dual, this is precisely an affine Demazure module from the title. So this is an affine Demazure module. And in particular, there's a Demazure character formula which permits one to compute what this vector space is with its weights and things like that. So this is very computable. This is an affine Demazure module, a space of sections on these affine Schubert varieties. Another remark is that the theorem of Joux recovers the Frenkel-Kac-Segal isomorphism by taking limits. Namely, the affine Grassmannian can be written as a limit of these affine Schubert varieties. So this is a strengthening of this theorem because it says something about spaces of sections on finite dimensional varieties. And moreover, this permits one to study the singularities of the affine Schubert varieties. So let me do an example of how this helps us study singularities. There's a short corollary that I should mention that helps with this. So if I have a torus acting on X, some scheme, or some maybe variety, with isolated fixed points, then X is smooth at P, fixed point. This will imply that the length of the structure sheaf of the T-fixed subscheme supported at P is equal to 1. Okay, so this is just a quick result that I'll show how we use in an example. So let me write down the affine Demazure module given by global sections on GER SL2 of 2 alpha 1 check bar with the ample generator dual. So this is computed using the Demazure character formula. I can kind of write it out in the with all the weights kind of written out as follows. It's kind of Fulton and Harris style description. So each of these top sections, maybe I can use color, each of these top sections can be described as sections which do not vanish, not vanishing at some t lambda. So in particular, this point right here corresponds to a sigma section not vanishing at T2 alpha 1 check, but vanishing at all the other T fixed points. This one corresponds to some section of the line bundle which doesn't vanish at T0. So section not vanishing here. So in this way, we can start getting a handle on what these weight spaces are. Oh, I should mention here that this direction in this diagram corresponds to the weights of the torus acting, and this direction corresponds to weights of delta. Maybe I won't say too much more about that at the moment. So what Joux's theorem allows us to do, so this is the these are the weight spaces associated to this space. So now Joux says this is isomorphic to global sections of GER SL2 to alpha 1 check bar T fixed L dual. And so this, remember, is going to be this can be viewed as the intersection of the T fixed subscheme with the Schubert variety. So this is a non-reduced scheme supported at T fixed points. And so in this description, these strings that we see here, these vertical strings, these maybe string, they're related to the string functions in COTS, for instance. These precisely give the lengths of this line bundle supported on these T fixed points. So for example, the length of O 2 alpha, there's kind of a lot of things to write. T supported at T0, this has length 6. There's a 6-dimensional vector space of sections that are supported on this T-fixed subscheme supported over 0. So what we immediately see here is that the point T0 is singular in this affine Grassmannian, Ger 2 alpha 1 check bar, SL2. So this is a way to study the singularities of affine Schubert varieties using this theorem. And so this reproves an older fact that affine Schubert varieties are singular along their boundary. Okay, I am frightfully low on time. Any questions here before I move on to the twisted setting?
Well, this is very different than what you would see in the finite dimensional case, because you would never, first of all, if you took the T-fixed points in a finite dimensional smooth thing, they would be smooth automatically. And
right, so this...
And here you're saying the T-fixed points being, and you're saying that nevertheless in this infinite dimensional case, even though it's true that the T-fixed points are not, I mean, it's, well, I mean, I guess, so, yeah, I mean, I guess it seems rather different somehow. I mean, but I mean, certainly you would never get in the finite dimensional case, you wouldn't expect the restriction for onto the T-fixed points of this line bundle sections to be an isomorphism anyway. That would certainly not be true.
That's true. That's true. If you consider something like finite Schubert varieties and you look at the associated short exact sequence, you'll get something very different. It'll look something like peeling off a W orbit. You're right. It'll look very different from what I'm presenting here. I will remark that these are finite dimensional schemes that I'm working with. But yes, you're definitely right that if I can make similar kind of short exact sequences or long exact sequences involving line bundles restricted to Schubert varieties, and I'll get things that are very far from isomorphisms. That's absolutely true.
The 6 is because the dot with the circle around it is a 2-dimensional thing?
That's correct. That's a 2-dimensional weight space that has delta weights -2. That's correct.
And not singular. I mean, it's singular because you didn't get 1 for the length?
Yes, it's singular because I didn't get 1. And so in particular, what I see here is that, well, it's already known that affine Schubert varieties are smooth, or affine Schubert cells are smooth because they're orbits. But a way of observing that is noticing that the length of the structure sheaf supported over the T-fixed subscheme, where these are points inside the Schubert cell, these are length 1. So you're kind of observing the smoothness from looking at lengths of the structure sheaf supported at points inside the Schubert cell instead of in the closure.
But I guess I don't know the answer to, I've never really thought about this, but in the finite dimensional case, so if you look at the T-fixed points
yes.
in the finite dimensional Schubert case, so I've always thought the T-fixed points in a finite dimensional Schubert variety would be reduced. Now I guess I don't know, however, off the top of my head, if the scheme structure for the T-fixed points would be the same if you consider them as a subscheme of the flag variety, or if you consider them as a subscheme of the Schubert variety, and then you take T-fixed points. But I know that if you have something smooth, then the T-fixed points of something, so I mean, I think they're always reduced even in I think the T-fixed points in the Schubert variety, I think are always reduced anyway. They always have a scheme structure there, I think, in the finite case. But here they don't, which is so surprising to me.
I think, I don't think that this is very well written down, but I think that if one takes a singular Schubert variety in the finite dimensional case, then one should be able to observe a non-reduced scheme structure on the T-fixed points there. When your Schubert variety is smooth, for instance, when it's the whole flag variety, then you're going to get something that's pretty well understood, namely this this is no longer an isomorphism in that case, it's just a map. And then you're just picking off one-dimensional you're picking off the extremal weight spaces of the representation in that case. I haven't thought about this too much for singular Schubert varieties in the finite case, though.
Yeah, I guess I'm wondering that if you, because whether you get two different scheme structures, like one is whether whether if you consider the point as sitting inside the Schubert variety, or if you consider it sitting inside the flag variety, you could get conceivably two different scheme structures. Yeah,
that's correct. If you view them as sitting inside the flag variety, then the flag variety is smooth, and then you're going to get reduced subscheme structure. The natural T-fix scheme structure will be reduced. However, if you take a singular Schubert variety, then I think you should have a natural non-reduced scheme structure on the T-fix points there.
Okay, yeah, that's an interesting question. Okay.
Yeah, excellent things, and this is something that I'd be happy to think about. Yeah, it'd be nice to see what exactly is going on for singular affine Schubert varieties in the finite case. Okay, the time is running a little short, so unfortunately, maybe my discussion of twisted things will be a little brief. So let me just mention, let me get started. So first we construct twisted loop groups. So twisted loop groups are going to be associated to diagram automorphisms sigma of G, or of the diagram. So I have, at the very beginning of the talk, I hid all my diagram automorphisms, but they're up here. So here are the finite Dynkin diagrams which have automorphisms, and I kind of wrote down what they are and what order we're taking them to be. There's one very important caveat, is that things are somehow always quite bad when one starts considering loop groups, or twisted loop groups, or twisted affine Grassmannians in the A2n case. So in this case, instead of taking just the diagram automorphism, I actually take an automorphism which is of order 4, which comes from the diagram automorphism, but it multiplies the simple root operators, or the simple root spaces associated to n and n plus 1 by I. So now I have an automorphism which is order 4 instead of order 2. This essentially kills one of the components of the affine Grassmannian, in this case, of the twisted affine Grassmannian, which is very poorly behaved geometrically. So here are my diagram automorphisms. If I let my automorphism also act on my base field, so I will kind of abuse notation here, but we also let sigma act on K by sending the uniformizer. Sigma of T will be equal to Xi T, where Xi is a primitive order of sigma root of unity. So I take an automorphism, I let it act both on my finite group and on my field, and I can take fixed points and produce twisted loop groups. So then the twisted loop group will be, at least on the level of K points, or C points, will be G of K sigma, and the twisted arc group will be G of O sigma, with some, one can make this schemy and have R points and things like that. But for the moment, let me just describe it in this way. And then we have the twisted affine Grassmannian, which is a quotient as before. So now I'll use kind of this beautiful G to denote this quotient, G of K sigma mod G of O sigma. And basically there's a robust theory either of groups over local fields or of affine Kac-Moody groups that are closely related. Well, all that I'll say is that we have very similar results that I had in the untwisted case in this setting. So for instance, we have the following. G will be in projective. I'll have the Picard group of beautiful G being isomorphic to Z here. Here I should probably take the neutral component. Picard group of the neutral components is isomorphic to Z, and we have an ample generator L of level 1. This is also something that is repaired by taking the order 4 automorphism instead of order 2. So basically, the twisted A2N case always behaves poorly, or totally ramified. SU of a totally ramified field extension can behave badly, is roughly what I'm saying here. What else do we have? We have that we can extend these to twisted Kac-Moody groups, affine Kac-Moody groups. Which I guess I'll write G tilde. This is probably very bad notation, but this central extension will then act on the cohomology spaces of the twisted affine Grassmannian and this line bundle L dual. So as we had before, we have to extend to get an action of some group on these cohomology spaces. What else should I mention? We also have a Cartan decomposition. Which I'll state briefly. Beautiful G is equal to a disjoint union. Essentially, all the combinatorics have to be replaced with things involving invariance or co-invariance. So sigma co-invariance on the co-weight lattice, and then I have L plus G of O sigma n lambda. This is the norm map, but yeah. So what I want to really emphasize is that modulo some changes that need to occur because of this automorphism sigma, this looks very similar to what we had earlier. Yes? Was that a question? Maybe not. So this now will be a twisted affine Schubert variety. I know that I'm running out of time, so I'll try to be. So terrible notation here, bar, bar, bar. So there's a lambda bar, which means I take the image in co-invariance, and then this is, oh, sorry, this is not closed. This is an twisted affine Schubert cell, beautiful G lambda bar. This is a twisted affine Schubert cell. I have the twisted affine Schubert variety, this thing is the closure of beautiful G lambda bar. And we have stratifications as before. So now beautiful G lambda bar bar, this is equal to a disjoint union overall mu bar less than or equal to lambda bar of the beautiful G mu bar. So very similar results that we had before. And moreover, lastly, we have an action of T sigma. Probably I need to take neutral, well, no, I can just take T sigma here. An action of T sigma on all of these twisted affine Schubert varieties, beautiful G lambda bar closure. So I have all the pieces that I need to set up a restriction morphism. So this is now the theorem. Well, we have a restriction homomorphism pi from global sections on the twisted affine Grassmannian lambda bar L to global sections G lambda bar, closures, T sigma fixed points L. And then the theorem due to Juzu and I, is that pi is an isomorphism. And as a corollary, we obtain that twisted affine Schubert varieties are singular along their boundary. I'm already definitely over, so let me stop here. I can say quite a bit more, but maybe at least this is a place where I can stop or pause.
So can you? I'm sorry, I think I missed. What is the definition of the twisted affine Grassmannian, and how does that sigma enter into the definition? Did you say that and I just missed it? Maybe the twisted
yeah, sorry.
I mean, is that like how does that enter? How is the twisted loop group defined? Is that just like an extension using sigma or something like that?
So the twisted loop group is precisely the sigma fixed points of the regular loop group, where I let sigma act both as a diagram automorphism and act on the field. So really the loop group could also be described as a form which splits over a totally ramified field extension of the loop group.
I see. Okay. So I see. Okay. So it's not, but so in other words, I mean, so should we think of it as kind of the analog of like a real form of somehow, not exactly a real form, but I mean, it's.
Yes, absolutely. So you can, if you want to work kind of p-adically, then for instance, in type A, these could be described as SU of some Hermitian form H, where this Hermitian form involves this totally ramified field extension C t to the 1/2 over C t, something like this. It's perfectly reasonable to think of these in that way. Yeah. And then the affine groups are various extensions of these, central extension and derivations and stuff like that. So H is a Hermitian form. On a vector space V. That and the yeah. Maybe I'll just stop here for that. Yeah. So it's perfectly reasonable to think about them in this fashion.
Are there any questions?
So then is this twisted affine Grassmannian, though, it's not like embedded in it's not a subset of the regular affine Grassmannian, is it?
No, it's not a subset, right? It's its own, yeah, I think just its own kind of homogeneous space
because GK sigma is a subset of GK, and
yes, but
if you took GK sigma and then you intersected it with like GO intersects, I mean, it actually looks like it would be in the. It looks like there would be a natural map of this into the affine Grassmannian.
Yes. So I think one thing is that in the maybe at the expense of maybe saying something wrong, I think the perspective from the Kac-Moody theory is that you could view this as a collection of fixed, well, yes, so maybe I'll say at the moment that I do not think of it that way, but maybe that's something to look at.
I guess it's because I'm sort of thinking, I'm just much more familiar with the finite case. I can think, for example, you can think of the real flag variety as sitting inside the complex flag variety, for example, or real projective space even as sitting inside complex projective space.
But it's being cut out by some interesting. It has some interesting variety structure.
Yeah, I mean, well, I don't know if that's a helpful way to look at that. Just asking.
Then I do not oppose a map of this into the untwisted guide, but that's not a technique that we used.
Any other questions? So if not, then let's thank the speaker again.
Thank you very much for joining.
Thank you for getting up early for us.
Oh yeah, no problem.
Yeah, thank you for an interesting talk.
Hopefully it was still clear and not hindered by